that. Yeah, welcome everyone to my presentation about integrating artifact translation into model transformation processes. You might be wondering that although I'm working in a team of Frank, there's no quantum computing in the title. So it's still possible, and let me explain a bit. So actually my research is in the area of software, quantum software engineering as well. However, when developing or deploying a quantum application, we run into some problems, and those are not like quantum specific problems. What kind of problems am I talking about? So let me give you an example. So now it doesn't work. So here you see a deployment model of a hybrid quantum application. We see, no, it's really not working anymore. A web application, which is the front end of our application, let's say, and this web application is hosted on a Docker engine, so it's a Docker container hosted on a Docker engine, and this connects to a Grow application, so this is our quantum application in the end, the back end, and I won't bother you with the details of the quantum application. However, this is hosted on a quantum computation as a service offering, simulator for Qiskit application here, for example. And what we wanted to do is to migrate this quantum application to a different hosting environment. So instead of running it on a Qiskit simulator, we wanted to run it on a PyKil simulator. So we could use model transformation for that, or just exchange this component, or node template in the Tosca terminology to speak. So we want to exchange this component to a PyKil simulator, and then simply as that, we could just send it to the deployment engine, and all the thing happens like instantly, right? So now this doesn't work like that. So what's happening in the background of the deployment engine, we need some deployment artifacts. So the source code of the quantum application, or could be any application, but we need the source code of the application, and this is, so this component here doesn't change from left to right. So this deployment artifact, for example, in our case, it was a Python script using the Qiskit SDK, so creating the quantum circuit, executing it. And if we just move it to the right side, this won't work. So we cannot just execute this part here. So this, the SDK with the Qiskit SDK, just execute it on the PyKil simulator. It doesn't work. Also, it doesn't work for like classical applications, just to move it into a different hosting environment. So what did we have to do? Either completely rewrite our application or write a translator, which we actually did. So we could have a translation going on from this Qiskit SDK, so this Grow application was translated from Qiskit to PyKil, both Python. But what we wanted to achieve is not to have two different steps, so not like first do the model transformation, afterwards do the whole translation stuff. What the question was how to combine both. So the research question for our work here is how can existing approaches for translating the individual artifacts be integrated into model transformation processes? So let me now give you an overview of our approach. So first we have our input model on top. This is, instead of now just focusing on quantum-based deployment models, we just use graphs. So these are typed graphs. And we do have the transformation rules, which do the actual transformation. So this is the basic of our approach. Now for each transformation rule, we validate them. So we validate all the transformation rules to find out which one are applicable and which one are not. From the set, afterwards we select one transformation rule to apply the transformation rule, and we find ourselves with an output. So the output is kind of different from the input. And in typical model transformation, we also are able to so we typically run multiple transformation rules, one after the other. So the output model becomes a new input model for the next iteration. Okay, so this is just a quick overview. Let's first focus on the input model. As I already said, it's a graph typed, a directed and typed graph. So for the sake of completeness, I added the meta model in here. The graph here is a tuple of 6 elements. Of course, we have the set of nodes, the set of edges, a set of node types and edge types, and 2 maps. So the type map and the super type map, which assigns, of course, these types to the single sets. Then we have the transformation rules. A transformation rule is a tuple again, consisting of a detector. So this detector follows the same meter model as I showed you earlier. It's also a typed graph here, and as well as the replacement structure and how it works. I explain later, but the detector will be replaced by the replacement structure, as the name says already. Furthermore, we have the set of translation mappings, whereby each translation mapping is a tuple again, pointing from the source artifact here to the target artifact, having a valid set of source artifact types, which is JSON and YAML in this example, the target artifact type, which should be XML, two optional attributes here, reference and properties. So I explain later what that means. Just for now, this is the transformation rule. And finally, we do have the set of edge mappings, also pointing from a source node to a target node, so source node, target node. We do have a valid edge type, which is any edge type. We do have direction, because edges have directions, and external node type. Also explained that, I'll repeat myself later on. Okay. So before going into the detail about the validation application, let's just assume this is our input example. So I want you to know how the output should look like in the end. So this is the output. So we have an input, two angularly shaped nodes with the circular node here in the middle, an artifact, or JSON artifact in here, and we said this detector, so this part here, will be replaced by this replacement structure, so by these three circular nodes plus XML. So in the end, translation is happening from JSON to XML in here, and all the edges are mapped, like I'm going to explain later, all the edges are mapped to appropriate nodes in the replacement structure. Okay, so now we know the, let's say, the details, and we want to focus on the validation of transformation rule. Let's go back first. So we have an input model, and for each transformation rule inside of this repository, we want to validate whether it's applicable to that input model or not. And this is done in 3 steps. First, we validate the detector. So for a transformation rule to be applicable to a certain input model, it has to be an isomorphic subgraph of that input model. So actually, in easy words, we just search for this detector in the input model. We can find it here, so this transformation rule would be applicable. Next, we validate the translation mappings. And for this, we include a second repository of artifact translators. It could be a service registry, for example. And from that repository, we generate a second graph, auxiliary graph, for example. So this just means that we have a translator T1 that is able to translate from YAML to JSON. We have a translator T3 able to, you get the idea, I think. And now we just have to check if our translation mapping, if we can find a translator from JSON was our example to XML, and we find here now T3 is able to translate from JSON to XML. And our approach, obviously, it's not just finding one translator, we can also do chain translations, and this is just finding a path inside this translation graph. Instead of letting our approach automatically choose choose all the translators, we can also reference a single translator to use. So just manually say, I want to use that translator for translating this artifact, and hand in some properties. So you might know in our example, we translate from JSON to XML. JSON allows to have multiple root elements. XML does not. So for example, so if we want to translate from JSON to XML, we need to wrap these elements in a wrapper element, and if the translator allows it, we can hand in a wrapper name for that font. So as an example. Finally, we need to, so we find T3, so it's valid. And finally, we need to validate all the edge mappings. So for a transformation rule to be applicable, all the external edges, explain next, all the external edges must be remapped by appropriate edge mappings. What do I mean by the external edges? So we see the detector here. This is the part of the detector in the input model. And the external edges are the edges that cross this border here. So later on, we remove the detector from the input model and replace it by the replacement structure. If we remove that, we do have dangling edges here. So those need to be reassigned somehow. And this is done by the edge mappings. So this edge mapping here says that all ingoing edges from any type and from any different kinds of external nodes, they will be remapped to this, reassigned to this node. And the same is done for the outgoing edges. So we can actually have, so this external edge is remapped by this edge mapping, and this external edge is remapped by this edge mapping. Okay, so now that we know that at least our transformation rule is applicable, we do this for all of the available transformation rules and identify now the set of applicable transformation rules. And from this set, we just select one transformation rule to apply. And yeah, for simplicity, this is a manual task in here, but in the paper we also gave some ideas on how to automate that step. If we selected one, we now want to apply this transformation rule, which is done in 4 steps. Don't be confused to read from right to left. I want you to just align it with the big picture here. So this is the transformation rule, our input model, and first we add the replacement structure, so the right part. We add this replacement structure to the input model, just add it. Afterwards we translate, so we apply the translation mapping, which means that we send our artifact through that computed path, translation path, so we send it through the path, invoke all the translators and fill in here the result of translation. Afterwards we apply the edge mappings, which means that this edge here before is now mapped to this here. So this was this edge mapping stating that ingoing edges to that node, so ingoing edges to that node will be remapped to this node here, to this node. Well, kind of confusing, but I hope you get the idea. And finally, since the detector has now no edges anymore, we can remove it safely and remove the detector, so we receive the output module. Of course, I won't go into detail here, but in the paper we also, of course, formalized it and have an algorithm for that. So, to summarize here again, we have the input model and the transformation rules, which we, in the first step, validate, or we check which transformation rule is applicable or not. Together with the artifact translators, we have the set of applicable transformation rules together with already computed translators used by the translation mapping. We select one transformation rule, apply it in several steps, receive the output model, and can continue on and on again. Okay, so let me now give you 2 exemplary use cases. First, of course, the use case I showed you earlier in the beginning. So the same deployment model, like in the very first slide, a quantum application hosted on a Qiskit simulator with the Grow application as a deployment artifact. And the transformation rule would look like that. We have the detector, which is a quantum application, just a type here, hosted on a Qiskit simulator, and it's getting replaced by the replacement structure, same quantum application, but now hosted on a PyKit simulator. And additionally, we do have a translation mapping between the 2 deployment artifacts, saying that any deployment artifact, so the source type can be anything, and we want to translate it to Python PyKit. So PyKit here. And of course, all the edges, so edges of all types and in any directions and from or to any type, nodes of any type should be remapped to this Parthian replacement structure. Okay, so this was the first use case, and for the second use case, in previous works, or in the previous work, we implemented a tool that is able to consume Python scripts and generate a quantum or generate a workflow. And we named it Script Splitter because it splits the script, identifies the quantum parts and the classical parts, and then generates a workflow, assembling all the original workflow from the Python script. And we want to integrate this want to use our approach to integrate this as a translator into model transformation, or into the transformation of a BPMN model. So let's say this is our workflow, so starting event. Now we invoke a script, which is a short application, so quantum application again. We invoke the script, print the result, have an end, and a transformation rule would, for example, look like this. So we replace the invocation of a script task with the invocation of a workflow. And of course, the implementation, so the show application, is now translated by using our script splitter. So we directly reference our script splitter and hand in some properties. I won't go into detail what that threshold here means, but yeah, exactly, we translate from Python to workflow to BPMN in the end. And the same thing as previously with the edge mapping. So what's happening is that the input model, or the part, the script here is sent to the script splitter, and what we receive is a workflow with a sub-workflow, sub-process here, so we work the workflow inside of it, and could include our script splitter then. Okay, a few words about discussion. This approach actually works on different abstraction levels. So the deployment model use case was like on the same abstraction level. We just translated from Python to Python, like the same abstraction level. But in the BPMN example, we had a lower level Python script and generated a high level workflow out of it. And it's also possible to have model refinement and so different abstraction direction. The translators that we included or integrated, they act as black boxes, so we actually don't see the details during modeling, of course, and this allows us also to have recursive model transformations, so a model by artifact translator. An artifact can also be a model can also be an artifact, so we can actually have recursive modeling transformations being done by the model by the translators. And it's also possible to hide confidential parts still in there, which is a nice thing. The sequence of transformation rules, so I said here that you can actually, or we actually run several transformation rules one by one after the other, incremental. This is, however, not commutative, but with the automation features, in the paper we gave some ideas how to automate, I said, and this is then kind of addresses this problem. And the translators, so we don't create new translators or create translators on the fly. They have to be somehow exist previously, of course. Okay, finally, to summarize, what I showed to you was how to integrate artifact translators into a model transformation framework. And I explained, of course, how the transformation rules work, how to validate the transformation rules, and how to apply them. I also showed some practical use cases. And in future work, so actually talking about the deployment model. So in future work, instead of just migrating during model time, we also want to be able to migrate running instances, so to be able to manage running applications and integrate these artifact translators within there. So, yeah, this is the end of my presentation. Thank you very much for your attention.
Yeah, thank you very much, Daniel. Then we will continue with our last speaker of today. The last presentation will be